In this presentation, I'll be explaining the power switch losses and heatsink design. What are the losses in the semiconductor switches as well as the design of heatsink. Now let us consider an ideal switch. An ideal switch, ideal switches are characterized by having zero voltage drop and zero resistance, and that is in on state condition. When the switch is on, its resistance is zero and the voltage drop across it equal to zero, and infinite resistance and zero leakage current in the off state. When the switch is off, it has got infinite resistance and zero leakage current. This is ideal switch characteristics. And practical switches depart from these characteristics, exhibiting a finite voltage drop and a finite resistance, forward resistance, and when switch is on, and there will be non-zero leakage current and when it is off. Therefore, this is the practical case. It is different from the ideal switch conditions. And if you see here, in an ideal switch here, this is a representation of an ideal switch in which when switch is off, the voltage across the switch is equal to Vt, or in here it is called V switch. And when switch is on, the current through the switch is equal to It or Ion. And the corresponding waveform for an ideal switch, this is the waveform or the voltage across the switch, and this is the current through the switch. Therefore, when switch is off, this is the voltage across the switch and current through the switch equal to zero. Similarly, when switch is on, the voltage across the switch equal to zero and the current through the switch is equal to what I on. Now, if you see the power dissipation of the switch here, the product of voltage and current, you can see that one here the zero power is coming. Here voltage is positive, current is zero. Here voltage is 0 and current is positive, voltage magnitude is there, product equal to 0. Therefore, in ideal switch, the power switching loss is equal to 0. Now we are going to considering the generic switch characteristics of a practical switch. A practical switch here, this is a simplified clamped inductive switching circuit diagram here. This is the voltage source, and here this is the switch representing the voltage across the switch or thyristor, whatever it is. When switch is off and then it is on, it is equal to It. And here this is the diode, and it's this represented across that one, say feedback prevailing diode as such, and this is the current source. Therefore, this is a simplified clamped inductive switching circuit diagram. Now we are going to plot the switching voltages here. What is the voltage across the switch Vt and what is the current through the switch for different instance. Similarly, this is the switching signal that is coming. That is here switch control signal is there. This is the on period, that is on period, and this is the off period, this T off, and the summation of on period and off period is called the total time period Ts, and which is equal to 1 by switching frequency. Therefore, this is the switching signal, and let us see what is the voltage across the switch as such. The voltage across the switch is here. This is the representing the voltage across the switch, and here when switch is off, the voltage across the switch is same as this DC voltage, that is the Vd. And at this instant, the switching pulse is given here, but it takes some time to reduce this voltage from the Vd value, and it is slowly going down to the on state, that is the voltage across the switch is getting reduced, and finally that is reaching to the voltage V on. And here the time reduction of this one from this to this one to reduce this voltage, that is called the fall time TFV, that is falling time of the voltage is taking here. Similarly, if you see the current through the switch, if you see that one, when switch is on, the voltage is getting down, it is reducing to the V0, here V on voltage, but current through the switch is increasing from here. The zero current was there when it is was off, and when pulse is coming, it is turning on, then the current is rising, and that is at this instant that is coming to the I0 value, that is, or It will become equal to I0, and this time this is called the rise time of the current. Therefore, TRI, and this is equal to TFV. Therefore, during this period, you can see that one, if you take this one, the voltage is reducing and here the current is increasing. And if you take the product of this voltage and current here, you can see that one, it will be like this one, that gives the power. This is the product of this current and this voltage. It will be the power, that is instantaneous power is drawn here. For the area under this one, or this area represents the during on period the switching loss as such, that the power loss, of course, that is represented by this area of this triangle. Similarly, and when the switch is on here, that is the voltage across the switch equal to V on, and the current through the switch is equal to I on. Of course, the magnitude of this one is very less, that is why it is negligibly small, that loss during the on period. And again during the off period, you can see that one, the voltage is building up. When switch is off, the voltage across the switch is building up from value to this one final, the voltage Vd. It takes some time, that one. Similarly, the current is dropping from this I naught value to the 0. It takes some time, and this is called the fall time of the current, and this is called the rise time of the voltage. And again, if you calculate the or product of the voltage and current, if you that will be giving again a triangle type, so figure as such. And this area under this one, that represents the, of course, the energy loss as such. It is actually power. We are plotting the power, and if you take multiplying the time, it will be energy. Therefore, this is the energy loss during the switch off period, and this is the energy loss during the switch on period, and this is the switching signal, and this is the voltage across the device or the switch, and this is the current through the switch, and for different instant is that's good. This is a generic switch characteristics. Now continuing the power switch loss here, same as we already seen this diagram here, and this is the energy loss during the on duration, and this is energy loss during the off duration. And here there are two timing is there. One we call is that current rise time. Therefore, the current is rising time, that is called current rise time. And similarly, voltage fall time. This time is called voltage fall time. And the sum of this one, current rise time plus voltage fall time, TFR, TRI plus TFE, that is called TC on. That is a turn on cross over interval, TC on. That is the summation of these two periods, that is TC on here. Similarly, then during that period, the energy dissipated in the device during this period, that is given by this triangle, or this area represents the energy loss during this period. Or that can be calculated as, since the area is representing, it is the area of this triangle, which is equal to half BH, or half BH means B is equal to the height of this one, which is nothing but it is equal to BD into half BD into I naught. BD into I naught is the height of this one, half BD into I naught into this time H is, that is, which is equal to this is a base, this is a height, H is this one, that is BD into I naught, and the base is equal to, of course, the TC on, and half BH, or half into BD into I naught into TC on. Therefore, this is the energy loss during the on period. Similarly, the off period, during the switching off period, the energy dissipation during the on state is given as this one, or that is already that will be explaining the next slide. Therefore, W's on, that is during the on period, that is the during this on period, the energy loss is given by what is V on, that is voltage across the switch when it is on, and what is the current through the switch when it is on, that is V on into I on. P on into I on into the time, that is the energy. V on into I on is the power, and that into time. Time is this T on period. That will be the energy dissipation during the on state. Therefore, during the turn on transition, it is equal to half VD I naught into TC on, and during the turn on, during the on state period, it is equal to W on equal to V on I0 into T on. Therefore, the energy dissipated in the device during turn on transition, which is equal to WC on, which is equal to half into VD into I naught into TC on. Already we have seen. And energy dissipation during the on state is given by W on equal to V on into I0 into T on. That is during this period. That is during this period. And since T on is very much higher than the TC on period or TC off period, TC off equal, this TC on and TC off here, and TC off is equal to, again I'm telling that TC off is given by the summation of these two periods. That is, of course, the voltage is rising and current is falling. Therefore, it is a sum of T TRV plus T for TFI. That is voltage is rising and current is falling. The summation of these two period is equal to the total, TC off aspect. For energy dissipated in the device during the off transition, again during this period, again you have to do the multiplication of the instantaneous voltage and current. Then you will be getting a triangle like this one, and you have to find out what is the area under this triangle, but that is the energy dissipation, which is given by again half BH. It's a triangle, half into base equal to TC off, and the height is equal to VD, of course the product of VD into I naught. Therefore half into VD into I naught into TC off is the power or energy loss during the off transition, during off turn off transition, and this is a during turn on transition. And the average switching power loss due to the transition is given by transition during that, is equal to half BD I naught into of course TC on plus TC off, that is the energy loss. And of course to calculate the power loss, that is multiplied, or it is equal to, that is multiplied the frequency, then we'll be getting the average switching power loss due to the transition. Therefore the switching power loss is proportional. So we can see that one, that as a loss here, switching power loss is proportional to the switching frequency and the switching timings. That is, switching timings means TC on as well as TC off. Therefore the switching power loss is a function of the switching frequency as well as TC on and TC off, or the switching timings. Continuing the switching loss, power switch loss as such. Here the average switch power loss due to the transition is given by half of VD into I naught into the frequency into TC on plus TC off, or the switching power loss is proportional to the frequency as well as the switching timings TC on and TC off. Therefore here the average, if the device with a short switching time, if this TC on TC off are less are available, it is possible to operate at a high switching frequency in order to reduce the filtering. If you are operating the switch at a very high frequency, then filtering requirement is reduced. Now, in order to operate at a very high frequency, these timings should be very less. Therefore, here for the same power loss, if you are reducing TC on and TC off, it can be operated for at a higher frequency so that the size of the filter can be reduced. Therefore, the average power dissipation on state P on is given by V on into I0 into T on divided by Ts. That is the during the on period, this is the power loss. So for V on is the on state voltage drop. For the leakage current during the off state can be neglected in practice. So the total average power dissipation PT in the switch can be, the total average power dissipation can be written as PT is equal to that PS, that is the switching losses, that is this one, plus what is during the on period, what is the losses is that. Summation of these two losses can be written as the total power loss of the switch PT, which is equal to half of VD into I naught into F into TC on plus TC off, that is this PS, plus when it is on, what is the switching loss, which is equal to V on into I naught into T on divided by TS. Summation of these two losses will represents the, or that gives the total average power loss dissipation PT in the switch. Therefore, the desirable characteristics of in a controllable switch, that is the one thing is that leakage current should be very small. That is small leakage current in off state. When the switch is off, the leakage current should be very small. That is the one desirable characteristics. Small on state voltage, that is when it is on, the voltage drop across the switch should be very small. That is small on state voltage V on to minimize the on state power loss, because P on equal to V on into I naught and T on divided by T. To reduce, if you are reducing this V on, that is when it is this one, you can reduce that P on to minimize the on state power loss. Short turn on and turn off timings, that is this time permits the device to use that high, that is if you are reducing the TC on as well as TC off for the same switching power loss, the frequency can be increased so that it can be operated at high switching frequency and the size of the filter requirement is reduced. Therefore, large forward and reverse voltage blocking capability, this will minimize the need for a series connection of the several devices. Similarly, high on-state current ratings in each in a high current application, this would minimize the need to connect in several devices in the parallel. For positive temperature coefficient and on-state resistance, parallel device share current equally. For small control power required to switch the devices. For large dV by dt as well as dA by dt writing of the switch. Therefore, these are the desirable characteristics of a controllable switch. Control of semiconductor device temperature. The theoretical upper limit on the internal temperature of a semiconductor device is intrinsic temperature Ti. The intrinsic temperature Ti, it is the temperature at which the intrinsic carrier density is most likely doped region of the semiconductor device equals the majority of the carrier doping density in that region. That we call it as intrinsic temperature Ti. In design small size, lightweight power electronic systems, the removal of heat and the control of internal temperature profiles are very important consideration. Therefore, manufacturers specify maximum junction temperature, that is, which is called TJ max. Typical semiconductor packages are designed at TJ max equal to 125 degree centigrade. Now let us see the heat transfer and thermal resistance. Power loss in a semiconductor device appears in the form of heat. Whatever we already explained in the power loss, no reason for power loss we already explained. And that power loss is appearing as a heat. It's appeared in the form of heat. The accumulation of the heat energy increases the temperature at the internal structure of the device. Temperature of the internal structure of the devices. Heat must be removed from the body of the device by transferring it into the ambient environment. And heat transfer in power electronic system is dominated by conduction and convection process. Thermal energy flows from the region of high temperature into the region of lower temperature. It is analogous to an electric circuit, that is, current is flowing from higher potential to lower potential. Similarly, the thermal energy that will be flowing from the higher temperature into the lower temperature. If you compare with an electrical quantity and with the thermal quantity, compare that one. Potential difference that is in electrical quantity, that is analogous to temperature difference in thermal quantity. Current through the signal or through the current through the circuit as such, it is equal to thermal power or rate of heat transfer, that is in watts. And electrical resistance, that is in ohms, that is equivalent, that is in thermal quantity is the thermal resistance, that is in degree centigrade per watts. Now let us see the steady state heat flow and the thermal resistance. This is representing the heat flow from the the chip, that is from this one, that is from the junction TJ and to the case, and then to the heat sink and to the ambient temperature. Therefore, the heat flow is in this direction. This is the heat sink, and that is exposed to the ambient temperature TA. Now, the equivalent circuit, if you see that one, for electrical equivalent, if you write it as, this is the power as a thermal equivalent circuit as a P here represents, and here Tj, that is the voltage as such, we can say that temperature of this junction, that is this Tj, and this is the case temperature Tc, and this is represent the temperature of the heat sink, and this is the temperature of the ambient temperature. And the corresponding resistance are between junction and case RJC, between case and heat sink RCS, and between heat sink and ambient, which is equal to RSA. Therefore, that is this heat energy that is going through this path, like equivalent thermal equivalent circuit is like this one. Therefore, the thermal power dissipation, that is in watts, which is equal to P, that thermal power dissipation, this much thermal power dissipation, that is equal to what is the junction temperature into the ambient temperature. That is junction temperature and ambient. Difference in this junction temperature and ambient temperature divided by the total thermal resistance between the junction and ambient. Therefore, RJ, that is the thermal power dissipation in watts. And Tj is the junction temperature, that is in degree centigrade, and Tj, or here Ta is the ambient temperature in degree centigrade, that is here, and the thermal resistance, the unit is degree centigrade per watt, that is the unit of thermal resistance, and which is equal to, just like a series resistance, summation of RJC and RCS and RSA, or RJA equal to RJC plus RCS plus RSA. Therefore, from this equation, we can get that Tj minus Ta, which is equal to the thermal power dissipation in watt, that into the total thermal resistance, which is equal to P into RJC plus RCS plus RSA. Now consider the design problem as such. A thyristor with a steady state power loss of 30 watts has a junction to the heat sink. Thermal resistance of 0.7 degrees centigrade per watts. Determine the value of the thermal resistance of the heat sink that can have, and if the ambient temperature is 40 degrees centigrade and junction temperature is limited to 125 degrees centigrade, give the base temperature at this junction. And give the base temperature at this junction. Thermal power dissipation P is equal to Tj minus Ta divided by Rj. That is this temperature minus this temperature divided by total thermal resistance. Total thermal resistance is given by Tj minus Ta divided by P. And here the temperature is given as here equal to 125. Junction temperature is to be limited to 125. Tj is equal to 125. Ambient temperature is equal to 40. For 125 minus 40 divided by, it is equal to the power loss equal to 30 watts divided by 30. That is the total resistance, which is equal to 2.83 degrees centigrade per watts. For thermal resistance, RJA equal to RJC plus RCS plus RSA. This resistance plus this thermal resistance plus this resistance. Or RJC plus RCS equal to, which is equal to this one equal to, that is given as 0.7 degree, 0.7 degree centigrade per watt. That is given at this one, 0.7 degree centigrade per watts. Therefore, the thermal resistance of the heat sink can be calculated, which is equal to RJA minus RJC plus RCS. Or here, it is equal to 2.83 degrees centigrade per watts minus 0.7 degrees centigrade per watts, which is equal to 2.13 degrees centigrade per watts. Therefore, this is the resistance between the heat sink and the ambient, or this one, heat sink and ambient temperature, or SA. And for temperature at the base, that is temperature at the base is given by 40 plus 30 into 2.13, which is equal to, that is here we can get that, ambient temperature equal to 40 plus, the R is equal to 2.13 degrees centigrade. That into, of course, here here 40 plus 30, that is the power dissipation into the 2.13, which is equal to 104 degree centigrade. Therefore, the temperature at the base is equal to 104 degree centigrade. Because here we can see that this is the, of course, the temperature, this can be considered as analogous to as a voltage, as we have already potential as such voltage. And here this 30 means that power dissipation, that can be considered as a current signals. Or this is the resistance, the product of the current and of course the resistance, that you gain a potential, similar thermal potential, something like that. Therefore, that 40 watts plus this one, that 40, 40, this is the 40 degrees centigrade, that plus 30 into 2.13, which is equal to 104 degree centigrade. Let us see another problem. Here, a 400 volt 960 amperes thyristor converter is supplying a load continuously. Determine the junction temperature with the following details. Ambient temperature is given by 40 degrees centigrade. Power loss equal to 150 watts. Thermal resistance between junction and case 0.15 degrees centigrade per watts. And RCS between case and heat sink 0.075 degrees centigrade per watts. And between heat sink and ambient, RSA equal to 0.45 degrees centigrade per watts. Therefore, this is the thermal equivalent circuit. And here, thermal power P is given by Tj minus Ta divided by Rj. That is given as, of course, that is equal to 150 watts. That's given 150 watts. Therefore, Tj Rja, that is the summation of this resistance. If you see that, if you Rja equal to Rjc plus Rjc plus Rcs plus Rsa, which is equal to 0.675 degrees centigrade per watts. For Rj we got it and P is got it. Then you can get what is Tj minus Ta. Tj minus Ta is given by P into Rja, which is equal to 150 into 0.675, 101.25 degree centigrade. That the difference in temperature of the junction temperature and the ambient temperature. which is equal to 101.25 degree centigrade. Or TA is already given as 40 degree centigrade. Therefore, from this one, you can calculate what is the junction temperature Tj equal to 101.25 plus 40, which is equal to 141.25 degree centigrade. Let us see another problem. For a thyristor, maximum junction temperature is 150 degree centigrade. The thermal resistance for the thyristor sink combination RJC equal to 0.015 degree centigrade per watt, RCS equal to 0.08 degree centigrade per watt. For the heat sink temperature of 60 degree centigrade, determine the total average power loss in the thyristor sink combination. In case the heat sink temperature is brought to 50 degree centigrade by force cooling, find the percentage increase in the device rating. So that is the question. Now first let us see the thermal power dissipation P equal to Tj minus Ts divided by Rjs. Tj is given as, of course, 150 degree and 60 degree heat sink temperature. Therefore, that minus Rjs, which is equal to 947.37 watts. With improved cooling, P is now P equal to 150 minus 50 plus 0.15 plus 0.1 equal to, by improved cooling, the temperature has brought to 50 degrees centigrade from 60 to 50. Therefore, the corresponding power is equal to 150 minus 50 divided, or that's to 105.63 watts. It was with cooling, the thermal power dissipation 105.62 watts. Thyristor rating is proportional to the square root of the average power. Thyristor rating is proportional to the square root of average power, or the percentage increase in thyristor power equal to square root of Tj minus square root of Ts divided by square root of Rjs. Or here the percentage increase in thyristor rating, that is equal to root of, it is increased to 1052.63 minus root of 947.37 divided by square root of 947.37 into 100, or 5.39 percentage is the percentage increase in thyristor rating because of the forced cooling, in which the temperature has been reduced from 60 degree centigrade to the 50 degree centigrade. Therefore, this much increase in rating can be obtained if you are reducing the temperature by forced cooling. Now one more problem is given. A MOSFET that is used in a DC to DC converter is dissipating 50 watts. The thermal resistance to the conduction from the junction to the case is 0.5 degree Kelvin per watts, and thermal resistance to conduction from the case to the heatsink 1.5 degree Kelvin per watts. And if the ambient temperature in the neighborhood of the heatsink is equal to 50 degree centigrade, then calculate the thermal resistance requirement of the heatsink if the junction temperature does not exceed 100 degree centigrade. Now, the thermal power dissipation P is given by Tj minus Ta divided by Rja. Therefore, here P is given by Tj minus Ta divided by the total thermal resistance. And Tj equal to 100 degree centigrade and Ta equal to 50 degree centigrade. Therefore, that is Rjc is given by 0.5 degree Kelvin and RCS given by 1.5 degree Kelvin per watts. And the total thermal resistance you can calculate, which is equal to sum of all this one. And the thermal resistance Rja, that is, which is equal to, applying this equation here, 100 minus 50 degree centigrade divided by 50 watts, which is equal to 1 degree centigrade per watts, or in degree Kelvin, which is equal to 1 plus 273.5 degree Kelvin per watts. Therefore, the thermal resistance required for the heatsink can be calculated, which is equal to Rja, that is the total resistance between the junction and ampere, minus what is the resistance of this summation of these two resistance, Rjc plus Rcs. Now, if you substitute here, it will be getting 272.5 degree Kelvin per watts. This is the resistance, thermal resistance of between the heat sink and ambient. Therefore, this RSA that is calculated.